8-bit address and represented in hexadecimal digits or hexadecimal digits, and each hexadecimal digit is having 4 bits. So we have, for instance, my MAC address is F0B8-2400-ABCD. So that's my MAC address of my PC. Let's say, for instance, that's my PC's MAC address. So PC's MAC address cannot be more than that. Okay, it cannot be more than that. It is 6 bytes long address. 6 bytes. So because we have 44, that is 1 byte. Okay, 44, another byte. Okay, 44, another byte, another byte. So we have up to 6 bytes. First 3 bytes represent the OUI, and the last 3 bytes, which last 24 bits, represent the vendor itself. So basically, guys, that is our MAC address. So like I said, MAC addresses are written. You can see we have letters combination with numbers, and MAC address is written in hexadecimal. And hexadecimal values are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And there is no 10. There is no 10 with hexadecimal, okay? But 10 is represented as A, 11 is represented by as B, 12 is represented by C, 13 D, 14 is E, and 15 is F. So, but if you want to convert these hexadecimal letters or alphabets to decimal or to numbers, you'll have to know what number value that they're equivalent to. So A equivalents to 10, B 11, C 12, D 13, E 14, and F 15. So now, how do we identify or how do we convert this to binary, to know the binary value of these hexadecimal digits? Okay, it's very simple. So here in hexadecimal, each hexadecimal digit is equals to 4 bits. Let's say, for instance, this 0 is 4 zeros, 4 bits. If you don't know what is a bit, it's a representation of the communication in devices. They use numbers because devices use numbers and numbers of zeros and ones. That's digits of zeros and ones only. So that is a binary representation of this number or alphanumeric numbers here. So that's it, hexadecimal. So we have to know how to convert from hexadecimal value to binary and from binary to hexadecimal. What will make it easy for you is that always have to remember something called the bit values of hexadecimal digits. The bit values of hexadecimal digits, I would just say we have 4 bits. So let's just say 4 bits per hexadecimal digit. So we start counting from right to left, saying 0, 1, 2, 3. So if you use a base of 2 here, 2 to the power of 0 is equals to 1, 2 to the power of 1 is equals to 2, 2 to the power of 2 is equals to 4, and 2 to the power of 3 is equals to 8. So what we are looking for here is these bit values. That is the number. And if you look at this number, if I combine it together, 8 plus 4 plus 2 plus 1 will give me 15. Because 8 plus 4 is 12, 12 plus 2 is 14, and 14 plus 1 is 15. So if you look at it here, it all ends at F. F is 15. So none of the values here would have more than 15 values. So you cannot have all the hexadecimal digits or values here would not be more than 15. So that's exactly what you're looking for. So now, how do we convert this? The simplest format is always use this 8, 4, 2, 1. This will help you. You don't need to use any form of square roots or something. It's going to confuse you. So the best thing is get this. And how I get that, I use this formula. Okay, so you can take, I'm going to explain this when I start talking about IP/4 conversion. So here I'm just going to make a rough one and a very quick one. So we just have 8, 4, 2, 1. So let's say we want to convert 1 into binary. How much is 1? What is the binary representation of 1 hexadecimal digit 1? What is the binary representation? It's simple. We take the value right there, that is 1. Okay, so we're going to say, can this value on the left, we're going to have to start minus, we're going to start subtracting. It's not a subtracting that you're going to do and say minus this, cannot but borrow that. Those mathematics are not used here. They're not laws that I use here. It is either it can go into it or not. If it can go into it, you will say yes, and then you put a 1 to represent that it is a yes. If it is a no, you put 0 to represent that it is a no for that particular value. Let's say, for instance, we would say, can 8 be subtracted from 1? If it cannot be subtracted from 1, we just put 0 on the 8. Means that 8 cannot be subtracted from 1. We move again, 4. Can 4 be subtracted from 1? If it cannot be subtracted from 1, it is simple, just put a 0, saying that 4 cannot be subtracted from 1. If 2 can be subtracted from 1, we put a 1. If it cannot be subtracted, we put a 0. Can 2 be subtracted from 1? We are moving from left towards the right. So 2 cannot also be subtracted from 1, we put a 0. Can 1 be subtracted from 1? Yes, 1 can be subtracted from 1, so therefore it is a 1. So the binary representation of 1 is 0, 0, 0, 1. That is it. As simple as that. Now let's take 2 for instance. Now, we're going to take 2 and say, we're going to find the binary representation of 2. Okay, can 2, so it's 2 right here. Can 8 be subtracted from 2? No. So we put a 0. Can 4 be subtracted from 2? No. We put a 0. Can 2 be subtracted from 2? If it can be subtracted from 2, say yes by putting 1 under 2 and subtract 2 from 2 and see what value you have. So if I subtract 2 from 2, I say 2 minus 2, I have what? 0. Now that 0 is my value, not the 2, because the 2 is already subtracted. Now that 0 that is left here, can 1 be subtracted from that 0? It's not possible, and there is nothing like cannot but borrow 10, remember? So therefore 1 cannot be subtracted from that 0, so it's a 0. So the binary representation of 2 is 0, 0, 1, 0. Now let's take another number, for instance 3. Alright, so guys, we're going to take 3. 3 is our next number, right here. Can 8 be subtracted from 3? No. So we put 0. Can 4 be subtracted from 3? No. We put a 0. Can 2 be subtracted from 3? Yes. 2 can definitely go into 3. Can it go? Yes. Put 1. If it cannot go, put a 0. But it can go. How many times? I don't know. I don't care how many times it can go. But I want to know if it goes, would there be any remainder? Yes, it can go. Now, 3 minus 2, how much? Are you left with? 1. Is there any other number in my binary? Yes, there is a number that is 1. Can that 1 here be able to subtract from that remainder of 1? Yes, then we put a 1. 1 minus 1, 0. That's 1 minus 1 is equals to 0. So it's done. So the binary representation of 3 is 0, 0, 1, 1. Now let's just go to a bigger number. Let's say, for instance, number 9. Okay, we're looking for the binary representation of number 9. So we're going to do this. Alright, so that's our number 9. Number 9 is my value. Is the binary, is the hexadecimal digit that I'm looking for. So it's binary. It's simple. Can 8 be subtracted from 9? Yes, it can go. So I put 1. See? Now, if I say yes, then I have to do the action of subtraction. So I will say, yeah, it can go. Then minus it. If I subtract it, I am left with 1. Yes, it can go. Then if I take it out of it, how much is left? 1. Can 4 here, that's the next value, can it be subtracted from this 1? If it can be subtracted, you put 1. If it cannot be subtracted, you put a 0. In this case, that 4 cannot be subtracted from the 1, so we have a 0. How about 2? Can it be subtracted from the remainder of 1? No, it cannot. How about the 1 itself? Yes, 1 can go into 1, so therefore it is 1. So the binary representation of 9 is 1, 0, 0, 1. That is a simple one explanation. Now let's go about A. Let's take A for instance, okay? What is A? Now we have to look at the decimal equivalence of A, okay? So the decimal equivalence of A is what? 10, okay? The decimal equivalence of A is 10. So now we're looking for 10. What is the binary representation of A? So we cannot convert A, but we have to look at what A equivalents in terms of numbers, and we do our calculation based on that number, not the A. But we still have to always maintain the A. There is no 10, there is no 11, there is no 12. So therefore, we'll say that 10 that represents the A, can 8 go into 8? Yes. 8 goes. Subtracted from 8, I'm left with 2. Can 4 go into the remainder of 2? No. Can 2 go into 2? Yes. remainder, so I'll say 2 minus 2 equals to 0. Can 1 go into 0? No. So therefore I have a 0. So the binary representation of A is 1 0 1 0. Okay guys, so let's take for instance D, and then our last portion will be F. So we're going to convert D and F, then we do the reverse. Okay, so let's take that. D is 13. Okay, D's representation is 13, so we'll say 13. Now we're looking for 13. Can 8 be subtracted from 13? Yes. If I subtract 8 from 13, I am left with 5. See? So I'm left with 5. Now my next option is that 5 is my value now, not the 13. The 13 is out. Now I'm looking for 5. Can 4 be subtracted from 5? Yes. Now I say minus 4 equals to 1. Now that 5 is no more my case. My case here now is 1. Can 2 go into that 1? No. But can 1 go into 1? Yes. So my binary representation of D is 1 1 0 1. Last bit is we're looking for F. Alright, so that's F. F is my next point. Okay guys, so F, the binary, the decimal representation of F is 15. So F equals to 15. That's how you're going to have to always remember this now. F equals to 15. So we're going to look for 15 in order for us to get the binary representative of F. Simple. So can 8 go into 15? Yes. If I minus 8 from 15, how much am I left with? 7. Sorry, 8 minus 15 is equals to 7. So 15 is normal. I am having only to deal with 7. Can 4 go into the remainder of 7? Yes. If I minus 4 from here, I am left with 3. Can 2 be subtracted from that 3? Yes. I have to subtract 2 from 3 or 3 from 2, and I'll be left with, let's say, equals to 1. So 2 minus 2 minus 3 is equals to 1. So can 1 be subtracted from that 1? I have yes. So therefore, my binary representation of F is 1, 1, 1, and 1. So basically, this is how you do the conversion of binary from hexadecimal to binary. Now let's do the vice versa. Let's do the reverse of things. Let's just make sure that, let's say for instance, we have a binary number that we need to convert into hexadecimal. It is very simple. How do I do this? I have my binary number. Let's say for instance, my instructor says, oh, Mr. Ali, I want you to do this. I want you to convert that for me in hexadecimal. I want to know the hexadecimal value of 0101. How do I do this? It is the simplest and the fastest way. Just make sure that you put the bit values on top of these binary numbers. I have 8, 4, 2, 1. This is 4 of them. Simple. Now, what do I do with this? Is that I am going to add the bit values of the binary numbers that have 1. Okay? This is 0 is for 8, 1 is for 4, 0 is for 2, and 1 is for 1. So therefore, the bit values in this scenario that have 1 underneath are the ones that I have to bind together. I have to add together to get the hexadecimal value. Now here, these are the 2 that has 1s. So what is the value of those? So it's going to be 4 here plus 1 right there. So I have 4 plus 1 gives me 5. So the binary representation of 5 is 0101. So you can do this in the reverse format, okay? You can do it. So let's say for instance also we have 1 0. So this is 3 1s and a 0. It is very simple with this. So you have 1 1 1 and a 0. So that's what we're looking for to sort out. It's simple. We put the bit values 8, 4, 2, and 1. So we look at the bit values that have 1 underneath. Okay? So we look at them. We have plus, plus. So we're going to add this. 8 plus 4 plus 2. Okay? They have 1s under them. So therefore their value is equal. So if I add 8 plus 2 plus 4, I have 14. 14 in hexadecimal is E. So you're looking for E, not the 14. Okay guys, so I hope you guys enjoyed this video. So I'll send you guys some questions to sort out for me on the WhatsApp page. So if you have any questions also on the WhatsApp, I want you guys to engage yourself a lot on the WhatsApp page, because we'll have to be busy asking questions and helping to answer some of the things that we may have. So guys, this is me, and I hope you guys enjoyed my video so well, and I'm just trying my best, okay? I'm trying to see what I can do. I don't have all the resources. I would have been on my laptop and do certain things, but unfortunately I do not have all the resources available, so I was just trying to do this. So I hope you enjoyed the video. Thank you.